Hi, I'm Sir Fernandez. I'm going to talk about running ROS2 on Android, iOS, and Universal Windows platform, and how it all came together. Um, I'm sorry, I'm not seeing the here. So here's a brief outline of what we're going to see. First, why I started this project, how the ROS2 architecture helped. We're going to have a look at the APIs and also some guidelines for adding a new language to ROS2 and some conclusions. So despite this being a talk about ROS2 on Android, iOS, and UWP, I want to explain a little bit about the history of this project. So I started working on this in late 2015. At the time, I was working at OSRF on ROS2. And as a hobby project, I wanted to get ROS2 running on the Raspberry Pi 2, but mostly on the Lego EV3 Mindstorm, which is, if you are not familiar with it, it's a robotics platform for learning. It's a platform for learning robotics platform. It's a platform for learning robotics, sorry, for children of all ages, including adult children. So single-board computers make a very compelling case for ROS2. ROS2 is all written in C and C++. It doesn't have a master, so network discovery is much simpler. You just add it to your network, and ROS2 will find your nodes. And there's no single point of failure. So imagine having a network of Raspberry Pis working together without relying on an external computer. ROS2 also has a low memory footprint. Memory is very expensive, so these boards don't have much. For example, the Lego EV3 it only has 64 megabytes of RAM. So the thing is that I got ROS2 built for the Raspberry Pi, but it took a couple of hours. This was on the Raspberry Pi. So imagine how long it would have taken on the Lego EV3. And then I thought, why not use a full-featured computer to cross-compile ROS2? I stepped back and looked at the big picture, precisely this big picture, which I'm sure you've seen many times already. So ROS2 structures each component in separate layers. It's like a lasagna, which doesn't mean that I'm saying that ROS1 is spaghetti. but in ROS1, transport, synchronization logic like threading, and client APIs are all in the same libraries. You see that ROSPy and ROSPP, there's no code reuse, and that causes some inconsistent behavior. So in the lower layer, we've got the transport implementations. At the time, there was only DDS with Connext, OpenSplice, and FasterTPS as vendors. Now there's NDN and Intel CPS, but this was 2015. We've got the middleware layer, which is the contract between whatever protocol we are using and the upper layers. We've got RCL, the client library, that provides a high-level abstraction. Provides a high-level abstraction of the middleware layer. Things that are not transport-specific go here as well, like time and logging. And then we've got the bindings layer, which contains routines for synchronization and the user APIs. So what was needed to cross-compile ROS2? At the time, the most complete implementation of DDS that had an open source license was OpenSplice, but unfortunately, its build system was a bit unconventional, and their public repository didn't have much activity. But good news, because OpenSplice was renamed to Cyclone DDS, and it's now part of the Eclipse Foundation. It also switched to CMake, and it's taking an open source first development model. I haven't had time to try it out, but I'm looking forward. Anyway, So as we saw, ROS2 is so flexible that we can change the DDS implementation. And here's where faster TPS comes up. It wasn't that mature, to be honest. It was missing some features. This was 2015, obviously. But it used CMake, and it had a fairly active repository. So things could only get better. There's something that Andrew Symington mentioned yesterday, that cross-compiling ROS1 is not very straightforward. And that changed with ROS2. One of the things that made it possible is the build system. Well, the build tools, actually. There's a distinction between build systems and build tools. Ament and Colcon workspaces can be easily relocated. There are no hard-coded paths when you build a workspace, unlike Catkin. And there's no devil space, which is so great. There were some minor things in ROS2 that I had to change, mostly minor fixes to ensure that the dependencies could be cross-compiled. And if you are interested, you can go to this repository and check out the scripts for cross-compiling ROS2 for the Raspberry Pi. But at this point, I wasn't happy. I wanted to do more, so I took a step further, and I thought, why not port ROS2 to Android, and eventually iOS, and then eventually UWP, and that's where I draw the line. For now. So you already know that these devices have plenty of sensors. The most recent ones, they even have depth sensors, thanks to ARKit and in iOS and ARCore in Android. Actually, this phone has a depth sensor. It's not a high-end phone either. And so imagine publishing point clouds from your phone. Would be pretty cool. And there's the HoloLens, Microsoft mixed reality device, which is pretty awesome. There are a couple of projects that bridge ROS1 with the HoloLens, but they use the web ROS bridge, and they don't put ROS inside the HoloLens, which is what I was aiming for. And after all, IoT and robots might not be that different. So if you are using Android things or Windows 10 IoT Core, you can also use ROS2. I have to say that for what C++ is, C++11 is great. It makes our lives easier, and it helps a lot when writing portable code. So ROS2 started at the right time. All these open source C++11 compilers were very mature, and therefore the changes, the two layers that were mostly left intact with all these changes were RMW and RCL. I only had to make a few changes, like for iOS. iOS 9 didn't support C11 thread local storage. That has changed in iOS 10. So anyway. But faster TPS is the part that required the most changes. It used to boost a lot, but fortunately we have C++11 and C++14. And for the parts of boost that are not covered in C++11, you can either find alternatives or write them yourselves. And that's exactly what I did. Faster TPS also, well, the RMW layer was missing type support in C. That's the thing that translates RTPS messages to C structures back and forth. And also something that I learned about iOS is that iPhone applications, they are statically built. They bundle all the libraries, which had a nice, so that wasn't possible with ROS1, but with the changes I made, yeah, it was possible with ROS2, and has the side effect that you can now distribute ROS2 applications, normal ROS2 applications, just without dependencies. You can just distribute the binaries. So with the foundations of ROS2 ported to Android, iOS, and UWP, we now need a way to access the RCL API from their respective languages, Java, Objective-C, and C#. I have to say that there are many ways to add a new language. The following is just how I did it for RCL Pi back when I was at OSRF. So I just repeated the formula for the other bindings. When you integrate a new language, you definitely need two things, a generator and a client library. The generator translates the MSG files into proper data types in the target language and converts from the C data types to the target language and vice versa. And also the client library, which wraps RCL into idiomatic constructs for whatever language you're targeting. He could also add support for the build system. Many modern languages have their own build system. You don't necessarily need to do that unless you want to integrate with AMENT and COLCON. The first three things are new in ROS2. Reverse dependencies in package XML files. The AMENT registry with which you can share data more easily between packages that use different build systems. Let's say you have a package that uses CMake and another that uses Python, and they can share information between the two. And also AMENT extensions, which are functions that are triggered when you call another function. The thing is that all these generators use the C generator. Under the hood, they use the generated C structures to interact with RCL, so you got to depend on it. When a message is used in the user API, it gets converted to the C structure in publishers and clients, and when a subscription or service take a message, they are converted to the target language. I'm going to show a few examples of the Java APIs. Just so I don't run out of time, because I could also explain about iOS and the other stuff, but anyway, I only have 3 minutes. So here for Java we have the standard. This is the part of the code that provides the standard setters and getters to store and retrieve internal data. But here there's something more interesting. These 4 static methods return a pointer to functions that will be called from JNI, which is the Java native interface. This might be a bit confusing, but we'll see an example when we get to the code for publishers. And this is just how Java messages are converted to C, and vice versa. Now, now you need a client library to interact with your with those messages. This is the API that your users will use. It's up to you how idiomatic you want to make it, but RCL makes it easy because all the functions are very simple. RCL has only has only 5 functions that are the minimum, like RCL init, RCL publish, RCL take, weight sets, and spin, and that's it. There's more stuff like services and quality of service, but that's the bare minimum. The 3 client libraries that I'm presenting each have a different way of interacting with C. So there's a chance that your language will fall into one of the 3 options, but we are gonna focus on Java. So when an entity is created in Java, in ROS2 Java, the underlying entities are located in C and stored as pointers, which are stored as integers. I use integers to store the pointers because it's just much easier to pass them back and forth between Java and C. And in C, I can just recast them back to the appropriate entities. And here's where it all pays off. Because this is C, all publishers are the same and cannot know anything about the type of the message they're publishing. So we obtain a reference to the Java method that we saw before. We call it, so we get a pointer. We cast that pointer back to the conversion function. And finally, when we call that conversion function, we get a ROS object. This is a conversion function that we saw earlier that turns Java code into C. The subscription part is fairly similar, but I'm not going to show it because I'll be running out of time. So the build system. Culkin and Amen tools, they're build tools that integrate build systems. They both come with support for CMake and setup tools for Python, but they can be extended to include more build system. That's yet another advantage for ROS2. You've got Java has Gradle and Maven, Ruby has Rake, Rust has Cargo, and so on. So adding a new build system is fairly easy, but things get a bit more complicated when those packages use some sort of they use ROS somehow. Like, for example, if they use the ROS dependency graph, or they have a package XML file. So in that case, you gotta put logic into the build system. So, for example, Gradle, which is a build system for Java. Gradle projects follow a fairly simple convention. They have a build Gradle file on top that describes the builds. You have a directory layout where that you have to put your code there for Gradle to find it. But however, integrating ROS Gradle projects into Ament and Culkan requires more logic. So more logic that needs to be put into Gradle, like configuring Gradle to output the appropriate directories, update the class paths with the dependencies that are declared in package XML, copy the jar files and the native libraries and bundle them together for Android applications. And if you are using a Java command line application, it'll generate launch scripts so that you can do ROS2, run, yada yada yada. Yeah. So here's an example Gradle project. We have the Gradle Ament plugin here, which will take care of everything. There's no special logic that you have to put into the Gradle file, and the plugin will know whether it's an Android application or a Java application and will act accordingly. But you don't need to do anything. We declare as a dependency, but if you are using a more recent version of Gradle, you can skip that. And we declare here an entry point so that the plugin will generate a launch script for our application. I'm going to show a few examples. I'm going to go pretty quick. I chose to present the examples similarly to ROS1, but composition is also supported in the bindings. They do the same structure. We initialize ROS2. We create a node. We create an entity, a publisher, and subscription. And we just let the event loop take control. That's likewise with Objective-C. It's the same. We initialize ROS2. We create the node. Unfortunately, Objective-C doesn't support namespaces, so I had to prefix all the messages with the entire namespace, which is not that pretty, but anyway. And the event loop takes control again. This is for RCL.NET. This is in C#. It's very similar to the Java example, with a publisher, with a description, and the event loop. And if you are wondering, yes, you can also use visualbasic.net with ROS2. Because some people just want to watch the world burn. I'm assuming, I haven't tested it, but I'm pretty sure that you could embed ROS2 in an Excel spreadsheet. But nothing good has come out of an Excel spreadsheet. And now for the clients and the services. Like with previous examples, we initialize ROS2. This is the service. We create a node. We create the service, which has a callback here, and we spin. And for the client, it's the same. And here's a thing that's different from ROS1. Client calls in ROS2 are asynchronous, so you can either use a feature or you can also use a callback function. I picked a feature here just because it was easier to read, but you can pass just a callback to that call. There's a demo here which I didn't do because I'm terrible with user interfaces. But fortunately, Emiliano and his colleagues at Ecumen, they took the ROS2 Android library and made an awesome joystick app that controls a Turtlebot that runs ROS2. There's no ROS1 here, and the nice thing is that actually the Turtlebot and the phone are using the same code base, which wasn't possible with ROS1. ROS1, you had ROS CPP and ROS Java, and neither shared any code at all. I'm gonna let it run a little bit because probably I still have time. And there we go. So, conclusions. With a good architecture, it's possible to target more platforms, even though ROS2 originally targeted macOS, Linux, macOS, and Windows. It's harder to tackle portability as an afterthought, so good thing. Portable code is usually of better quality. It requires you to lay out your code in a better way. ROS2 is really modular. Many of its pieces are swappable. For Android, iOS, and UWP, I'm not using many of the standard ROS2 repositories because I don't need them. I can just focus from the language layer back to RMW, and that's it. And Ament and Colcon are definitely an improvement over Catkin, both for cross-compiling, but also for integrating all build systems. And portable code benefit a lot from mother language standards. Here are all the links of all the things that I did. There are some other things that I haven't put in there because there were just minor changes, but this has been the work of the last 2 years. So, and thank you.
All right. let's get, there's one back there, and then Jack.
Thank you very much for your work on the adding new languages to ROS2. It's very important. And I have a question about the recent development in the Oracle licensing for Java. So, they would be charging for the updates for their proprietary Java. Have you heard about it? Do you have any recommendation? Are you testing over OpenJDK your code, or you're using Oracle Java?
I gotta say that in my day job, we don't use Java at all. So I'm not caught up with the news about Java, to be honest. But if anything, I heard about that and just use OpenJDK.
Okay.
Forget about Oracle.
Fair enough. Thank you.
So for iOS support, why did you use Objective-C instead of Swift?
Because it's easier to bridge Swift on top of Objective-C than the opposite, at least back then. Also, I found Objective-C slightly easier to understand coming from a C background. So yeah, but just you can still use Swift in the same way that you can use VisualBasic.net with RCL.net. You can also use Swift on top of RCL Objective-C.
You mentioned that Ament and Kulkan are improvements over Catkin, which I think is true, but also a comment and I think a reasonable critique of what we do in the ROS world is that we build our own tools. As you were integrating with the tools that come with other application areas, other languages, did the tools that we built provide a benefit there, or did that make it more difficult to integrate with things like Gradle, the fact that we had this existing infrastructure that had to be plugged in somehow?
Well, I chose to integrate it with Ament, so I knew what was coming. But the thing is that I think the problem is not with the tools itself. It's more about community outreach. People don't see the value in these tools. They don't see the problems with Catkin because Catkin just works. Yeah, it just works until you want to cross-compile ROS to ARM, or until you want to integrate a different build system. So, in my opinion, the tools are good. It's just we need to do better. We need to reach out to the community better and explain why. I'm hoping that with this talk, that I showed that, yeah, Catkin was good up until 5 years ago, and Ament and Kulkan are a huge improvement. At least for my use case, they were.
Okay. Thank you very much.